Cool. Thank you, Patrick, for that warm introduction. Hello, OBTS, and thanks so much for attending this talk. If we haven't met, as Patrick said, my name is Jaron, and I work with Jamf Threat Labs. So we've done a number of talks here in the past, and this year I'm excited to bring you something that's a little bit different, which is that of a research project we've sort of been poking at maybe 1 to 2 years now. That's tied to data science around Mach-O executables, so particularly executables that have already been determined to be malicious by various vendors out there. So I started putting together a bunch of content for this talk, and after I had done that, I noticed that really everything I wanted to show off wasn't so much focused on the data science. In fact, there was a good handful of data science I noticed talks here already this year, and I wanted to save room for that. So instead of focusing on that portion, I wanted to focus on what the analyst can actually do with the outcome of that data science. Basically, a way to dive into the applied use cases rather than just the science itself and you know how to do complex things. I think we'll hear about that from some other talks coming up. So you might think you're looking at a strangely sci-fi backdrop, but the tool you're seeing here is in fact a portion of our malware database mapped into 3D space. So to give a quick oversimplified breakdown of what's going on here is our data science team goes through our malware database, and they have ways to compare all the samples in this database to each other. For example, for each piece of malware, they provide us with an XYZ vector, and we're able to plot that into 3D space, resulting in an interface that we call Titan. So in theory, the more similar a sample is to another sample, the closer it should be to that sample in 3D space. I get a lot of questions on the interface and what it is, and the answer, it's a custom interface we built with Three.js specifically for this sort of analysis use case. So using Three.js is basically a standard when dealing with 3D content in a web browser, and it's been used in many different data science projects before, but this one was manually built by us. So that was a 1-hour talk summed up into a paragraph so that I can focus on the actual applied use cases. And from here, it will be 100% demo. So may the demo gods shine upon us in their favor. All right. We're going to come back to this. I know the big question, is it going to work? All right. Let me adjust this mic stand so I can still see my computer. All right, so what you were looking at here is this is, once again, what we call Titan. It's fully interactive, so we can kind of poke around in here and click around. And just remember, each and every individual node that you're seeing on the screen here represents an individual piece of malware. In this particular sample, we have a couple different versions of Titan. So one you're looking at here, I'm going to zoom a ways out. You're looking at one here on the left. This is built using ASM to VEC. ASM to VEC you can read the research on. It's basically where you can look at the assembly of the executable and basically compare that to other binaries so long as you're comparing that assembly. So we have that on the left side. And if I kind of scroll into this and I start picking some stuff, I don't know, I'll just I'll grab a cluster that's nearby here. We can see that we can select it. We can sort of, look around at it. We can increase the size of this radius to kind of select multiple nodes and multiple pieces of malware. And then we also have the ability, of course, to then be able to investigate that, right? So inside, down low, we'll have the table of the different samples that we've selected. I can see here that this is a cluster of what looks like ad agent or multiverse according to the vendor consensus. So within the selected samples, here's what we sort of choose to display. I don't know how hard that is to read for everybody in the room. I know we go back a ways, but we have the hash of the executable. We have what we at Jamf would call that executable, or what malware family we would call that. Then we have the vendor consensus. just to kind of see what everybody else is calling this. We have Yara, which is one of the main reasons, and I'll get into this in a second, one of the main reasons we use this tool is actually to kind of determine how our Yara coverage is faring out there. And then that reminds me, I have to note this is a outdated data set, so don't think anything about the unknown Yara hits. We have lots of Yara coverage, and this is an older data set rather than a completely up-to-date one. So, but that also gives me the opportunity to show you how we've used it over the year. And then we have the architecture of the executable, and then finally we have the signing. Well, it says signing ID. That's technically the team ID or the developer who signed the sample if one was used at all. I can see that these are all, in this case, unsigned. So that's just kind of a breakdown. For us, we of course want to make sure that when we're detecting on malware, yes, being able to block by the team ID is great. Yes, being able to block by the hash is great. But in a best case scenario, you want to be able to block by Yara. You have better coverage that way. There's a good chance that if you can detect one sample, you can detect multiple samples, in this case, via clustering, which we'll take a look into. So that's sort of just a basic of some basic details of the table. Now I'm going to go over to the other Titan instance as well, because this is also relevant. I'd mentioned that the other cluster is ASM to VEC. This is more of a custom rolled KNN, if you will. So we're looking at static features of the files, and then we convert from the data science, once again, to the 3D vectors. But we're looking at static indicators on this side of the universe, if you will, rather than the assembly code. So a lot of things people lock onto pretty often. I'll randomize the colors here to try and get, yeah, there we go, that's a little brighter. A lot of things that people lock onto is this strange figure right off the bat, right? And you say, what is that figure? And I say, that's not a figure, that's a space slug. And behind it is another, if you look, a little baby space slug. But essentially, these are really interesting, and these are kind of a good example of where data science is pretty cool, because I believe we've done some of the analysis on how this thing sort of formed. Oh, there we go. We did some analysis on how this thing sort of formed, and based on the static indicators, this is, if I select the kind of big one over here, and I look at the table, I see that this is all bundler malware, or adware, if you will. Not that interesting, but it is abundant, right? There is a lot of it inside of this database. So, but if you were to look at the samples, go and grab them, and you kind of compare them, you'll see that there's sort of random bytes added to each of these malware samples, and that's how we get this very strange, very large space slug, is because every sample is ever so slightly different. It's not identical. If it was identical, the node would be placed right on top of each other, and instead we get this very strange looking object, right? As for baby space slug, if we take a look back here at baby space slug, and we take the coloring, I should note that the coloring right now is reflecting what we at Jamf call that malware name. So everything with the bright green would be called bundler. We call it bundler. I can change that coloring to instead be based on, say, the developer ID. And as I can kind of see here, again, I'm going to randomize the colors and hope we get something that hits that black backdrop a little better. There we go. I can see here that these are all unsigned, which we saw on the table. But with the baby space slug back here, if I can get to it, there we go. I know that's a little harder to see on your screen. But if we look at the small one, we see that these are all signed by different vendors, right? Every single node is a different color. So potentially picking up on that info also where every file is a slightly different size, but at the same time, it is also every single file is signed by a different vendor, which we can see here on the far right, where we see that nothing really lines up. It's all different. So again, that's just us kind of exploring the data, making interesting sort of notes. We are also able to sort of filter this data. Yeah, we can color by any color that we want, or we can color by the different fields, but we can also do, if I set that back, we can filter as well. So I can say something like, okay, in this malware database, show me all of the ARM malware. right? And we see that a lot of stuff falls off the grid. Again, we're looking at, let me reset the color to see if we can spot that on the screen. But if we do that, I go look over here. I see there's plenty of it. It's not showing up well on the screen. We can sort of see it in the background here. I'm not sure if you can pick on that, what's coming up over here, but there's samples, and there's quite a few. But Intel has been around, obviously, significantly longer, right? We've seen Intel malware for a long time. Now we're using universal binaries that come with both ARM and Intel, so every universal binary that comes out, we still have the Intel binaries. So all that to say, we have a massive amount of Intel malware, and ARM is still catching up. Probably will still be catching up for quite some time, even after Apple decides to drop Intel. So let me reset the filter. And we also, another filter that we could set just for the sake of it is to show kind of samples. Oh, nope, reset filters. Here we go. We can show all samples, all malware samples that are not signed. We see not much changes, right? There's a lot of signed malware out there, and yeah, like it did disappear. The scope of this graph has actually shrunk, but in reality, it would seem like just by looking at this graph, the majority of malware is still being signed, right? Or is not being signed. Apologies, that was misleading. So none of these examples have shown why this visualization is overly useful yet, right? We could have done these lookups using some standard queries instead of clicking around and trying to view things, right? So let's get into some use cases of where this has actually, where the visualization portion of this has actually helped us. I'm going to go back. I'm going to go back over to the ASM2vec side of things. And one of the most useful cases, again, it has come a lot around Yara coverage. So let me find my mouse. If I go to I'll show a handful of specific examples that I handpicked. We're going to go look at this particular cluster. And if we look at this, let's randomize the colors a little so it jumps out. That's good enough. And let's get rid of the selector so we can see. If you look at this, we have a group of pink, right? And that's based on what we are calling that malware. But there is one here, as you can see, it's red. And that tells me that, hey, like something's going on here where I'm detecting this cluster of malware as a certain family, but there is one oddball that's sort of standing out, right? And we do this with the colors. We go through, we look, and we see, okay, there's one oddball, it's an anomaly. Let's kind of, let's dig into that a little bit. So if I go look at the table, based on everything that's selected here, I see that, no surprise, we're once again looking at atomic today, right? So I have a cluster of atomic stealer. And then if I scroll through this, I see that I technically have 2 unknown hits here. So I would want to tune this Yara rule to actually pick up on these unknown hits, because it's telling me that based on all the malware that's out there, I am technically missing in this cluster. My Yara rule is missing something, and who knows? That's just what's in this database, right? There could be 3,000 samples out there that go hand in hand with the 2 samples I'm missing here. So I want to adjust my rule to hit on everything in a cluster for the best coverage. And again, this is a fundamental use case that we use it for. I can give you another location inside of this ASM2vec Titan where we have a similar situation. We see this sort of linear cluster here that has one pink item among a bunch of green ones, and it's the same situation, a little less severe this time because it is more an adware scenario with bundleor. Where unknown, in this case, is right up here. We can see that this sample is not detected by our Yara rule, so once again, we want to tweak that to try and make sure that it's covered. So one of the things we'll sometimes do once we find something we're interested in, we can pivot with that hash from from one model into the other. So I can go take a look at what this sort of looks like within the KNN model. I can see I have a very light color there, but if I randomize it, we can see it. And it's kind of interesting, this bundle or sample from a static perspective of indicators. I mean, it's there, it's hanging out with all the other bundle or, but it's kind of by itself. It's sort of an oddball. Like, it's not really clustered anywhere. We still know it's bundle or, but I don't know. That gives me an interesting result. I might want to look into this. Maybe it's packed. Maybe there's something tacked on the end of it. I don't know. And that's kind of what we use this tool for, is finding interesting things to then pursue and look into. All right, I'm going to go back to ASM to VEC. Now I'll do kind of the same thing, but we'll combine some of these searching and filtering to do some more kind of threat hunty type approaches. So I often, another thing we sort of like to do, don't mind me bouncing around here for just a second. One thing that I like to do is I'll do something like, okay, let's take a look at what other vendors are seeing out there for, let's say, Amos, right? Again, we've talked about it a lot today. Let's filter all the samples that are Amos. There are a fair number in here sort of floating around. We do see that there's some larger clusters. Randomize the colors, there we go. We do see that there's some larger clusters kind of hanging out, and these are all atomic stealer. Again, there's been a lot of it that has come out this year, and it kind of leaps out, right? For malware that hasn't been around on macOS that long, like, there is a lot of it. So I might want to look at where the vendor consensus is Amos, and where also on top of that, our Yara hits are also unknown, right? This is going to give me something to pursue. This is going to tell me that, hey, there's clusters in here that are not being detected by us, and we want to make sure those are taken care of. So here's kind of a cluster. Got a few samples that are a little far away. I got a few samples that are brought together, but I'm still willing to bet that based on all these, as we can see, they're all Amos. If I can detect one of these samples with Yara, I could probably pick up this entire cluster with the same Yara rule, and I now have a place to kind of start from, or a sample set to kind of start from to build out this Yara set. So if we kind of follow that same idea, coming in with specific hashes that we're trying to find interesting clusters, let's take a look at this one. This is a fun one. We see there is this one just hanging out all by itself. Remember, we filtered data. It's kind of close over there to that cluster too, but in reality, it's fairly far away. So this one is hanging out all by itself. I do this a lot, where I'll go and I'll find a single node of a particular malware family that's just by itself, and then I'll remove all the filters. And we see that, sure enough, this is actually not by itself. There's just a bunch of other malware that's hanging out near it. I'll put this selector back on really quick, and we'll just select kind of this whole section here. But if we go and look at the table, I can see that this is filled with a lot of different malware, but it's all labeled generic. It's all labeled multiverse. I believe multiverse for some vendors is the same as the word generic, if I'm not mistaken. But what this kind of tells us is that this cluster that's starting to get rather large, maybe at the time, vendors didn't really know what to call this cluster. Maybe they didn't know it was Amos. Maybe Amos wasn't out at the time. I can't remember where this exact data set came from date-wise. But people don't really seem to know what it is yet. But because we've found a single or maybe two atomic steal samples within this larger cluster of generic malware, we can probably assume that if it is indeed atomic, everything in this cluster is atomic. And I would then research that to see if, like, hey, are other vendors maybe mislabeling this, or have people just not figured out what it's called yet? One other use case I'll show off here is Shikata Ganai encoder, if you're familiar. This has been around a long time. and been used for a long time, but it was most heavily used and most infamous with Metasploit, which we don't see a lot of these days, especially for macOS. But I think something interesting about this is it kind of let us see how ASM-to-vec sort of treats encoders. So with Shikata you could take like your executable, and although that executable might be detectable at a hash level, or you can just grab the indicators out of it, with Shikata you could kind of wipe a lot of those indicators out, change the hash, and make it harder to detect. I think in theory at the time, like impossible to detect, right? But with ASM-to-vec, we actually see that there's a lot of different colors in this cluster. There's even more kind of up here that are also green, right? But if we just look at the different malware families in this cluster, we see there is Git shell, which is a lot of vendors are just call that Meterpreter, I believe. And then we see that there's also hits on Shikata. So in other words, this shows us that ASM-to-vec is able to kind of pick up the fact that even though a file's been encoded, it still falls inside the malware family cluster before it was encoded. And we tested this with our own binaries where we dropped them in and then we'd encode it, drop it in, and they'd still appear next to each other, which is pretty cool, but your data set has to be large enough. All right, last example that I will show off is that of Beavertail. Patrick did a blog post on Beavertail, I think earlier this year, probably not even that long ago at this point, to be honest. But if we take a look at Beavertail, I'm gonna shrink this down a ways, and then let's get rid of the selector and randomize colors. What do we got? There we go. So this right here is Beavertail. We see that it's right here in the middle of this giant sort of, right in the center where stuff does not cluster super nicely. So our question was, after Patrick's write-up, the consensus was kind of that Beavertail was tied to Lazarus Group in some way. So our question naturally, like, hey, like without us doing anything except for using Titan, ASM-to-vec, et cetera, can we determine that this sample is tied in any way to Lazarus, right? That'd be really cool. We would not do any type of automation around attribution, but we certainly would love to use it to see if it could, in theory, work that way. So that was kind of the big question we had. So we dropped that in and did a look for it. I'm going to turn the selector back on and kind of just expand this a little. Let me make sure it's the only thing I have selected at the moment. It is. So if we expand that a little, I don't know, I'll give it 3 hits. It looks, here we go. Yeah. If I look down, I see that it clusters, and again, cluster might be a rough term here, so, but I see that there's a lot of minors. Not overly interesting to me. I don't believe Beavertail was, can't recall if any way it had some type of minor built into it. I don't think the answer was yes to that, so I can't make any assumptions off what's going on there. But I did note, oh boy, please hold, that wasn't supposed to happen. All right, but I did note that if we sort of increase the size maybe one more step, and one more. There we go. If we do increase the size by one more step, we do see that we have apple juice sitting relatively close to this particular sample, apple juice being a Lazarus backdoor. So like we don't have perfect clustering, but that would have been in the radius that we have here in this sphere, which in the terms of what we used, like we would have picked up on that where we saw, oh, like this is kind of close to a Lazarus sample. We should maybe check out what's going on there. So we grabbed that particular sample and just kind of compared it to the other malware. Beavertail compared to that sample that we saw sitting kind of close to it. And then just to be clear, sorry, I lost it again. It's the problem with live demos. There we go, apple juice. If I take this hash, you know, we kind of have a way, we set up a way where we can also measure kind of the distance from one sample to the other. So I'll take that hash, and then I'll go there, and then I will get rid of the selector and hit go. we can see, I mean, those are not that far from each other in the greater picture of this huge sphere, right? So although it's placed kind of with minors, it's still, we're going to call that close enough where we'd like to look into it. So we pulled it, we did kind of a bin diff. Sometimes you can get lucky, you know, this is unsupervised learning, it's very experimental, but sometimes you can get lucky and you can find functions that ASM2Vec is probably basing this assessment off of. And in this case, we had one on one side in the malware that was called set base browser URL, and one inside the other the Beavertail sample that was called rule removed clicked. And we found a handful of these. I don't have time to go through them all, but we found a handful of these where even looking at the flow chart, right, you can see very, very similar with some added logic right there. Bin diff coming in handy there. Looking forward to using that Ghidra mod. Yeah, pretty sweet. Just a little bit. We can take that a step further, obviously, by doing manual analysis and not assuming that data science is going to do all of it for us. Okay, so that is Titan. We have a lot we're still learning about it. It's not open source or anything like that, really. We just wanted to share some examples of, hey, like using like existing data science methods and executables in a big database, like you can build stuff like this, and in reality, it's not all that difficult, especially if you have a team of people that are able to dedicate their time to it. So with that, I also wanted to sort of note one more thing before I jump off and Patrick shoots me in the face with a Nerf gun here. But that is a fact. I've also been hard at work trying to get another book out the door. Thank you to all of you that have told me my book has inspired you in some way. It's meant the world to me. I'm still quite a ways from finishing it. I do plan to self-publish with this one. So if you see me post on LinkedIn or X, please feel free to, retweet whatever as I try to figure out what this self-promotion thing looks like. All right, I think I'm out of time, so I'm going to jump off. Thank you, everybody.